Hello, everyone. In this lecture, we're going to discuss classification models and primarily the logistic regression. My name is Hui Yang from Department of Industrial and Manufacturing Engineering at Penn State. So this is an outline of this lecture. We have talked about predictive modeling using the linear regression so far. In this lecture, we're going to look into logistic regression and multi-class classification. So as we can see here, descriptive modeling, we can derive descriptive statistics. That means the summary statistics from the data, including different kinds of statistical measures, central tendency, dispersion, right? The other group of pre-analysis is data visualization. You can, descriptive analysis is data visualization. You can do histogram, normal probability plot to check whether the data follow normal distribution or not. Or the scatter plot, try to check the relationship between two variables. Now, classification problem. For example, if you receive an email and you want to classify it into spam or not spam. So those are the decisions, binary decisions you want to make. So online transactions, is it a fraud? Yes or no? A tumor, malignant or benign? Okay, is it good or bad? So binary classification, we have two outcomes. Y, response variable is 0 and 1. 0 is negative class, that's benign tumor, or 1, positive class, malignant tumor. And in addition to the binary classification, we also have multi-class classification. For example, you have multiple classes. For example, so we have binary classification and multi-class classification. Now let's move on. So in this case, we have a tumor size. So x-axis is tumor size. And the y-axis is, we want to build a classification model to classify it is yes or no based on the tumor size. Okay. You see here, we have the short x-axis. Then we have a group of we have some data points over here, some data points over here. And you can fit a linear regression model y equals to x beta. Okay. And then you will have a threshold 0.5 and you will have a cutoff right, let me use a pen, right here, okay? However, if we have more data points, for example, the data point is right here, and then you have more data points here, and you're gonna fit a linear regression model like this, then you will have a cutoff right here, right? And based on the tumor size, you're gonna predict it's malignant or not. So we can threshold the classifier output and P X beta at 0.5. If it is greater than 50%, it is malignant. If it's less than 50%, it's negative. Okay, now let's, oh, I cannot move on. Okay, I can move on. Now, suppose we have an outlier over here, then we have some kind of problems. So regression problem, if we use regression to solve this problem for the classification, for the binary classification, we have either 0 and 1. But if we just use P as our response variable, but regression, because we have X beta, right? X beta is beta 0 plus beta 1X. And it could be greater than 1 or less than 0. So we want to develop a formula that can constrain the response variable to be the probability we find this tumor is malignant or not, actually in the range of 0 and 1. So regression model is not a good model. So that's why we are developing a logistic regression model to predict the probability to have a malignant cancer. And so this is our new formulation, logistic regression for a classification problem. So binary target. For the binary target, we don't want to use a direct line to fix it and to fit the data. We want to use the logistic regression like this curve. And we want to limit this curve in the range of 0 and 1 so that the probability don't go outside the bound, right? So linear regression does not work because whatever the form of the equation, the results are generally unbounded. Instead, you work with probability that the event will occur. So let's interpret the probability x beta. This is the estimated probability that y equals to 1 on input x. So if the x is, if you have a intercept and so you add a x0 and x1. So if the probability is 0.70%, then tell the patient the 70% chance the tumor to be malignant. So probability equals to 1 given x parameterized by beta. So probability y equals to 1 given x beta plus probability y equals to 0 given x beta. This, because we only have 2 outcomes, so this added together should equals to 1. So probability y equals to malignant, yes, is actually the opposite of 1 minus, it is not malignant. So now let's have a look at the formula of logistic regression. Let's see, this is page 7. Now let's get into slide number 8. In linear regression, we have y equals to beta 0 plus beta 1 x1. So this, if we only have one predictor, this is a simple linear regression. If we have multiple predictors, it will become multiple linear regression. If we write it in the matrix form, y equals to x beta plus epsilon. And then what we are trying to do is we minimize the residue sum of squares. So this is a residue square sum, so residue sum of squares. We minimize this and then we use a normal equation as we discussed in the regression module, linear regression module. But now we are going to use the probability, right? Probability, because we are doing the classification. What's the probability y equals to 1? What's the probability y equals to 0? And because based on the total probability rule, there are only 2 possible outcomes. So one is P, the other one, success is P, and the other one, for example, this is malignant, not malignant, is 1 minus P. So we know the odds. If we do P over 1 minus P, this is the odds. Okay. Now we're going to do the logistic regression. Logistic regression equation is this one, log P over 1 minus P equals to x beta. And the x beta belongs to minus infinity to infinity. Is in the range from minus infinity to plus infinity. And the P is in the range of 0 and 1. And the odds is in the range 0 plus infinity. To get familiarized with this range, please visit the exercise. We have a logistic regression exercise, which actually describes the range from P to odds. If P is 0, 1, and odds, what's the range of odds? Odds are actually 0 plus infinity. And then the log odds. So this is the log odds. And because the log odds equals to x beta, if we expand this equation from this equation, we will be able to solve for P and 1 minus P. Because we put exponential on both sides, we got an exponential x beta, and then you solve for P, it will equals to this one. If we know P, we know 1 minus P, right? Now, odds instead of probability. In the logistic regression, we are modeling the log odds as the x function, right? Use the x beta. So we are using the odds instead of the probability. P is the event occurring. That is a horse losing a race. 1 minus P is a probability of event not occurring. So this is a binary classification, spam or not spam, malignant or not malignant. So the odds of the event happening is actually P loss over P win. So this will be P over 1 minus P. So 19 to 1 non-shot at the racetrack, the ratio 19 to 1 means that the horse has one chance of winning for 19 chances, right? So the probability of winning, so 19 over 1 equals to P 1 minus P. So 19 minus 19P equals to P equals to 19 over 20. So 1 minus P will be 1 over 20. So the probability of winning, so 19 to 1 non-shot. Ratio 19 to 1 has one chance of winning for 19. Okay, for 19 chances. So this is about 5% to win. Has one chance. In total, there are 20 chances. He has one chance winning for compared to 19 chances. So 1 over 20 is the probability of winning. 19 over 20 is the probability of losing. The odds is actually 19,001, 19 to 1. So we discussed this one in the exercise before. So if we have P, so you see the x-axis, this x-axis. Let me use the laser pointer. This x-axis is actually my probability. So probability only goes from 0 to 1. So we have two bound, right? So if we look at odds P over 1 minus P, this is actually in the range of from 0 to infinity, because we have P, that is a possibility that P equals to 0. So this should be in this way. So this will be the odds curve if we have P here, and this curve will be log odds. So the log odds highly negative for low probability P. So when the probability is less than 50%, you see it goes from minus infinity to 0, and highly positive for high probability of P. That means it goes from 0 to infinity. So in this way, you see we have a probability a cancer to be, a tumor to be malignant, right? And then we convert this P to odds. This odds goes from 0 to infinity, and then the log odds go from minus infinity to plus infinity. We know that linear regression, y equals to beta 0, 1 plus beta 1, x1. The right-hand side goes to minus infinity to plus infinity. The left-hand side also needs to go from minus infinity to infinity. So that's why we need to transform P into log odds. So this equation, P equals to 0.5, and then we calculate odds. Odds equals to 1, so this is 1, and log odds, log 1 equals to 0. So this is why it's right here. Now, logistic regression prediction formula is actually log odds equals to beta 0 plus beta 1 x1 plus beta 2 x2. This is called a Logit score, also called log odds. So if you take exponential on both sides, the P actually equals to 1 over 1 plus exponential minus x beta. 1 minus P is this one. So the odds is actually equals to P over 1 minus P. So this is exponential x beta. So if we put this whole thing as x beta, then let's put this whole thing. Let's write this right side to be x beta. Then we put an exponential on both sides. Then you can solve for P. This is P. And if you solve for P, you can know 1 minus P. And then odds is P over 1 minus P equals to exponential x beta. Log odds actually equals to x beta. So this is the logistic regression formula. And now let's have a look at the logit link function. Let's go to the next slide. we know that P belongs to probability has to be in the range 0 and 1. Let me use my pen because it can reach 0 and 1. And the odds is 0 to infinity. And the log odds is from minus infinity to infinity. Now it makes sense because the right-hand side and the left-hand side and right-hand side, both of them, the right-hand side can go from minus infinity to infinity. And the left-hand side can also go from minus infinity to infinity. The Logit link function. Logit link function is if you have P, you put Logit right here, Logit, okay, this is Logit. This will be the Logit link function. This is actually Logit is actually equals to this one. You transform P into this way. So you transform the probability between 0 and 1 to Logit score between minus infinity to infinity. So this is a basic formula of the fundamental difference between linear regression and logistic regression. Logistic regression use a Logit link function, that is log odds. Now, how do you estimate the parameters? Previously, we have residual sum of squares, and you do the minimization of the residual sum of squares. For binary classification, we're going to use likelihood function for logistic regression. So binary classification, the probability of yi equals to 1 and the probability of yi equals to 0 is 1 minus probability p xi beta, because there are only two outcomes. One is p and the other one is 1 minus p. Because either yi equals to 0, 1 minus yi equals to 1, or yi equals to 1, 1 minus yi equals to 0. So we have the likelihood function. So for any xi, suppose you have n samples. For any xi, you can calculate the probability. So you have 1 here. This is 1 minus p. So if yi equals to 1, then this part will disappear, right? Let me use the highlighter. If yi equals to 1, then this part, because this is 0, yi equals to 1, 1 minus yi is 0, so this part will be 1. So this is the likelihood. If yi equals to 0, this part is 1, and then you got 1 minus p. So this is likelihood. Okay. So you want to maximize the likelihood. So this is called MLE, maximum likelihood estimation. The log likelihood turns products into sums. So now you take the log, L beta. So if you take the log yi goes to the front, then you have log p, 1 minus yi, log 1 minus p. And then we know that p actually equals to exponential xi beta, 1 plus exponential xi beta, because this is what we derived here, right? And 1 minus p is this term. So if we put this into this equation, then what we are going to get is you have log xi beta. So this will become yi beta transpose x minus log. You just put these two equations. Put 1 minus p into this one, and put this into here, and then you expand it. It will become this term. Now we got the likelihood function. We need to maximize this likelihood function. To maximize likelihood function, we set the first order partial derivatives of L beta to 0. So for every beta, you just take the partial derivatives and then set all of them to 0. And then you can use numerical algorithms like Newton-Raphson algorithms to search for the minimal. Search the beta that will give you the minimal. Give you the maximum, because this is a maximal likelihood function. Whenever you have derivatives to zeros, then you will be able to reach the maximum. Now let's have a look at this pool. Linear regression on a binary target is a problem because the prediction can range outside 0 and 1. Is this right or not? Yes, this is right. Because this is a problem. It can go outside of 0 and 1. Now let's have a look at the standard logistic regression. So this log odds, and you put it in this way, beta 0 plus beta 1, x1, beta 2, x2. And you have x1, x2, and then you have the, this is a probability, right? This is a response surface. Now the log odds like change like this. And you can also have the quadratic term. Because this x1 and x2, this log odds only change with respect to x1 and x2 linearly. So you see the linear increase. But if you want to have nonlinear response surface, you actually can add the quadratic term. So in this way, you will be able to get the quadratic surface. So you see log odds changing this way. You can also increase in this direction. So accounting for nonlinearity, so logistic regression, you can add the quadratic terms. So this one only the linear hyperplane, but this one, if you add a quadratic term, you can add a little bit of nonlinearity in the model. Now let's have a look at an example. This example is about the credit card default. And let's first have a look at the descriptive analysis. So you have two variables, predictors. One is the balance, the other one is income, the balance of the credit card and the income of the credit card holder. You see the balance and default or not default, right? Default, yes or no. And for the balance, it's actually well separated. Okay, for those who default, you used to have a lot higher balance. So this is a scatter plot. You plot x1 and x2, and you try to see the distribution, and you see those are the no default account. Those are the default account. So in this way, there's some outliers. And as we can see, the distribution for non-default, the balance pretty used to be low, and high, the default account pretty high. But for income, it's not very much separated, right? So now with these two variables, can we predict the default or not binary outcome? Suppose for the default classification task that we code, can we use linear regression? Now let's code y equals to 0 and 1. If not default 0 and default yes, linear regression might produce probability less than 0 and or bigger than 1. So logistic regression is much better. So it constrains our outcome to be within the range of 0 and 1. So linear regression, unbounded. Linear regression does not estimate the probability of default very well. Unbounded, minus infinity to plus infinity. Now let's use the logistic regression. P actually belongs to probability of default. It's actually in this range. So log odds equals to x beta. So now we decide to use the logistic regression to build the classification model. We use the maximum likelihood, and because P is actually just yi equals to 1 and y equals to 0. So this actually equals to the multiplication of Pyi, 1 minus P, 1 minus yi. It's similar to, it's the same as what we just discussed, maximum likelihood estimation. This likelihood gives the probability of the observed zeros and ones in the data. So we pick beta 0 and beta 1 to maximize the likelihood of the observed data. And most statistical package can fit a linear logistic regression model by maximal likelihood estimation. In R, you can use GLM function. And in MATLAB, it's also a GLM function. So this is after you maximize the likelihood, take the partial derivatives. If you want to know how to do it, then you use partial derivatives with respect to beta and then set it to 0. And then you try to maximize the likelihood. Or you can use different algorithms to search for the maximal. And after we use this function, you can estimate beta 0 and beta 1. This is beta 0, this is beta 1. And you can also estimate standard errors and these statistics, and both of them are significant. So here we used only one predictor balance because we found that the income is not a very good predictor. So now, after we got the beta 0 and beta 1, now how do we do the prediction? What is our estimated probability of default for someone with a balance of $1,000? So you do the probability of x equals to exponential beta 0 plus beta 1x, and 1 plus exponential beta 0 plus beta 1x. Now you put the value in because beta 0 is minus 10.65 and beta 1 is 0.0055, so times 1,000. So the probability is only 0.6%. With a balance of 2,000, the probability of default is 58.6%. Let's do this again using student as a predictor. Okay. Now, if we have a data, if we have data of whether the credit card holder is a student or not, and then we can still fit this model. Suppose this is the parameter we got, and we can put these parameters into this equation. So given it is this person, credit card holder, is a student, what's the probability of default? And this is probability. And given the student is not, given the credit holder is not a student, what's the probability of default? This is 0.292. So this is another example with another predictor. So here, the previous two examples, one used the balance as a predictor, the other used a student as a predictor. We can use multiple predictors. For example, log odds, and in this side we have multiple p predictors, and this is then we can still calculate this. Suppose we have beta 0, beta 1, beta 2, beta 3. We use 3 predictors: balance, income, and a student, whether it's student, yes or no. This is 0 and 1. If we go back to the previous slide, you see, student yes is 1, student no is 0. So for this predictor, the value is only 0 and 1. Then we can estimate the coefficient and all the statistics and see which one is significant. Obviously, balance is significant. This can be validated with a scatter plot or box plot. We see that balance is a good predictor, but income is not. You see previously, let's go back to the income. The income is not a good predictor because you couldn't really use income to predict default or not. So that's why the p-value is greater than 0.05, 5%. So the smaller the p-value is, the more significant the parameter is, or the predictor is. Again, the smaller the p-value is, especially when it is less than 0.05, then the more significant is the predictor. That means the predictor give us more discriminatory power to predict our response variable, default or not. Student is the same. It's a sensitive predictor. Now, so far we talked about only the binary classification. What about the multi-class classification? For example, the email folding, tagging, and you have work, friends, family, and hobby. You have 4 classes. When the email comes, you want to automatically put them into different categories. Our medical diagnosis, not ill cold, and flu. So you have 3 categories. Weather, you have sunny, cloudy, rain, slow. So you have 4 categories. So binary classification, you have X and Y, you want to classify them into 2 categories. But multi-class classification, you have X1 and X2, you want to classify them into 3 categories. So how to do that? And the idea is you do 1 versus all. For example, for this class, you do it 1 versus all. You establish 1 logistic regression. And then you rotate to this 1 versus all. And you get the second logistic regression model. Then for the third class, you do 1 versus all. You got the third logistic regression model. Okay, so this probability tell you what is the probability to belong to this category. This model tells you what's the probability to belong to this category. And this model actually tells you what's the probability belongs to the class 3. If you have more classes, you can continue to build 1 versus rest logistic regression model. Now train a logistic regression classifier for each class to predict the probability that y equals to I. On a new input, to make a prediction, pick the class I that maximizes the probability. Because you have, if you have 3 classes, you will have 3 logistic regression model and 3 output. What's the probability belongs to each class? You just want to choose the one that give you the maximized probability. If we go back, you have 3 models. So this is a very interesting and smart ways to do the multi-class. So 1 versus the rest. So you got an input, you just calculate 3 probabilities. Whichever is the maximal, you classify the input that belongs to that category. So now we have finished the multi-class classification. The reading assignment, please read and review chapter 4 of the textbook in details. This is the end of this lecture.